Right, this week we're just going to do one section, 3.4. As you can see, this is my favorite theorem that we cover in college algebra. I'm so sad that we can't do this in person, and I can show you how to use the calculators and everything, but we will do our best. All right, so I want to start off. We are going to use this rational zero theorem. This is a very important theorem. So it starts off by outlining or defining a polynomial function. And so I'm going to write it above because that's a little small and hard to read. Okay, a polynomial in general form has a series of coefficient a sub n's, and the x's are in descending power, and the subscript of the a sub n matches the superscript of the x's, right? And we talked about those just being the coefficients. So here is the polynomial in general form. Now we're going to focus on the constant a sub 0 and the leading coefficient a sub n, right? So when we start factoring our polynomials, like this one, I want you to know that there are three types of zeros, all right? And so the three zeros that we can have rational zeros, which is what this theorem is all about. Now, rational zeros are any zeros that can be written as a fraction, positive and negative. So we're looking at, -2 is a rational zero, 6 is a rational zero, 1/3 is a rational zero. Okay, those are the first types of zeros that our polynomials can have. The second type of zeros that our polynomial can have are irrational zeros. Now, irrational zeros, the only way to find those is with the quadratic formula. So these are the zeros like 1 plus or minus square root of 5, where the square root can't be simplified. Or we can get, -2 plus or minus the square root of 7. All right, those are all irrational. These decimals do not repeat and do not terminate. So we can have these kinds of zeros in our polynomial functions. Both of these types of zeros will show up on the graph. The rational zeros are really easy to estimate from the graph. The irrational zeros, not so easy to come up with. So if you have to state the irrational zeros, you're going to have to make sure you can show all your work the way I'm going to show you in just a few. So the third type of zero are the complex zeros. And these zeros are complex numbers. These are the imaginary zeros, 1 plus or minus 3i, okay, or just, 4i plus or minus 4i. These zeros also are found with the quadratic formula, and they occur when we have a negative underneath the square root symbol. So if this is like a -5, we would have the square root of -5, so we'd pull the I out, and we get 1 plus or minus I squared to 5. Those are complex zeros. Now, complex zeros do not show up as x-intercepts. The only way to find them is through dividing out all the rational and irrational zeros and using the quadratic formula to come up with the complex zeros, right? So we are going to focus on the rational zeros and using those rational zeros to factor our polynomials. So the rest of this theorem says if this polynomial with integer coefficients, so we can't have fractions for our coefficients, they have to all be positive and negative whole numbers, then every single rational zero is of the form P over Q. So we're going to talk about this P over Q list. This is a fraction. P is on top, Q is on the bottom, right? And where P and Q are integers. Now, what is the P? Okay, P is a factor of the constant, right? So we're going to look at the constant. We're going to find the factors. What are the factors? So if the constant was 4, the factors of 4 would be 1, 2, and 4, because factors are any number that divides 4. right? And so we're going to put all the factors of p on the top, and then q is a factor of the leading coefficient a sub n, right? So all our q values are going to come from a sub n. So a lot of times I'm going to put p colon, I'm going to list all the factors of the constant here, q colon, I'm going to list all the factors of a sub n here, all right? So we're putting the factors of the constant over the factors of the leading coefficient. That is going to come up with a list of all the possible rational zeros. Now, all the possible rational zeros may not work. Okay, they might not be actually zeros of this polynomial. But if the polynomial has any rational zeros, they'll be in this list, right? So now that because everybody doesn't have a graphing calculator, I am going to kind of switch up how I want you guys to show your work here. So I'm going to try and adapt my teaching to the lack of having handheld calculators and just using those online ones. But we are going to come up with this P over Q list a lot. All right. So we're going to go ahead and jump right in, guys. We're going to using the rational zeros theorem. Yes. So find the rational zeros of P of x equals x cubed minus 3x plus 2. So the first thing I want to do is I want to list the possible rational zeros. So I'm going to come up with a plus or a minus P over Q, and this is really important, okay? The theorem just says use P and Q, but factors could be positive or negative. So I'm going to make sure I do plus or minus for each P over Q I find. So P is the factors of the constant. So the constant is 2, and the factors of 2 are just 1 and 2. These are going to be my numerators, right? The leading coefficient, the Q values, the leading coefficient here is 1. So the factors of 1 are just 1. So when I come up with this list, I need to find all the possible combinations here. But only the P values go on top, and only the Q values go on the bottom. So this list is actually fairly short and fairly simple. I'm going to put 1 over 1, and then I'm going to put 2 over 1. So I get plus or minus 1 over 1, and plus or minus 2 over 1. Right? So how many zeros are here? This is an important question, because this is what the question is going to be on your final exam. Right? So how many possible unique rational zeros are there? We have 1 and negative 1, 2 and negative 2. So even though you just see 2 zeros here, because we have plus or minus, we need to multiply that result by 2. So we're going to have 4 possible rational zeros. Now total zeros, okay? All the rational, irrational, and complex zeros. If I were to ask how many zeros will this polynomial have, right? The degree is what's going to tell you that. So because this is an x cubed, the degree of this polynomial is 3. It is going to have 3 zeros, max. Right? It won't. Not all of these will work. Okay. So I need to find 3 zeros. If I find 3 zeros, then I can write those zeros as factors. So typically what I have you do is I have you plug these into the calculator. All right. So let me just show you once with my calculator. Okay, so here we go. I'm going to turn it on. If you have a graphing calculator, great. Make sure you're following along. If you're going to use the online calculator, just hold off for a moment. Right? If you have your own calculator, go to your table set menu, okay, which is above window. So second window will get you your table set menu. Make sure your independent variable is set to ask. This is going to allow you to auto-build your table. It's not important that the 0 and the 15 match, just that your independent variable is set to ask, dependent is set to auto. All right, so now I'm going to go to y equals, right? And I'm going to plug n, the polynomial, into y1. So let me clear this function out, right? And I'm going to go ahead and type in this equation, x cubed minus 3x plus 2, right? So how can I use the calculator to tell whether they're zeros or not? When I plug the numbers in, I should get a y value of 0. So what I'm going to do now is I'm going to go straight to the table, right? And table is here above graph, so second graph will get me the table. Now remember, this table you can reuse, and so what I'm going to do, get the glare off, what I'm going to do is I'm going to type over these values, right? Our zeros are 1, -1, 2, and -2, right? So I know that if the y value is 0, then we have a 0. Because if the y value is 0, remember these are the remainders, right? If I plug 1 into the polynomial, I get a 0 remainder. If I plug -1 into the polynomial, I get a remainder of 4. So I'm really looking for the numbers that give me a 0 remainder. Because if the remainder is 0, then they are indeed zeros. So I'm going to write those down, okay? I know I have zeros. 1 worked, and -2 worked. Okay. Now that's only 2 zeros. This polynomial has 3 zeros. So what happens if you find all but 1, what's going to happen is one of these zeros is going to be of multiplicity. One of these zeros has got to work again, all right? Because if it can't be a different 0, or else we would have found it in this list. And it can't be irrational or complex because those occur 2 at a time. They always occur in plus or minus pairs, right? So we have 2 zeros, only 1 left. Okay, it has to be one of these numbers working again. So what I want you to do, right, and you're going to do this on the online calculator as well, is I want you to look at the graph. It's really hard to get this glare off. Ooh. Oh, let me change my window. Okay, I think I'm going from -1 to 1, and it's not really looking good. So window, I'm going to change this back to normal. There we go, that's better. Here comes the polynomial, right? Notice we can tell it's a cubic, right? Because the end behavior is opposite, has a positive leading coefficient because it's going up. And here's the zeros, -2 and 1, right? So how can we tell whether it's a 0 of multiplicity? Well, if it crosses the graph, it's odd multiplicity, meaning it's probably just multiplicity 1. If it touches the graph, we know that it's even multiplicity. And so most of the time, this means that the multiplicity is 2, okay? So -2 works once, and +1 works twice, okay? +1 is a 0 of multiplicity 2 because the graph is touching here. So what I'm going to do is I'm going to list 1 again, right? And I'm going to list 1 again because the graph touches the x-axis at 1, right? Because graph touches x-axis at 1, right? So here I have a 3rd degree polynomial. I found all 3 zeros, and so if I want to, the question just said find the rational zeros. Done, okay? So you do probably want to list the multiplicity again. If you put a list of just 1 and -2, the online homework probably will count you wrong. They want to see that you know the 0 that 1 is a 0 twice, okay, because the graph touches. Now I want to take this one step farther just so we keep practicing it. I want to write the zeros as factors because the whole goal is to be able to factor higher degree polynomials, all right? So I'm just going to write each one of these zeros as a factor. So if 1 is a 0, x minus 1 is the factor. If -2 is the 0, x plus 2 is the factor. And again, if 1 is a 0, x minus 1 is a factor. So if you would like, you can go ahead and write this as x minus 1 squared times x plus 2, okay? Where you can see that the multiplicity of this factor is a 1, and the multiplicity of this factor is 2. So the graph is going to touch at 1, and it's going to cross at -2. Now, because not everybody has a graphing calculator, I'm not going to expect to see you do the table every single time, right? If you want to just put your polynomial into the calculator and then look at the graph, if you can find all the zeros from the graph, more power to you. But be careful, it really needs to cross at those whole numbers. Anytime it crosses in between, the guessing work there is really hard to guess the right fraction, because it could be an infinite number of fractions in there. So I'm going to kind of show you how to get those using the table. All right. So let's go ahead and work more examples. All right, example 2. We have this polynomial, okay, 2x cubed plus x squared minus 13x plus 6. Okay, write it in factored form and find all its zeros. I like to find the zeros first and then do the factored form second. So the first step is to figure out how many rational zeros it has, right? So I want to come up with this list plus or minus p over q. These are the possible rational zeros. Not all of these are going to work, but if they work, if the polynomial has a rational zero, it'll be in this list. So first I'm going to come over to the constant. This is going to tell me what the values of p are. So I need the factors of 6, all the numbers that divide 6, right? 1 and 6, 2 and 3. So 1, 2, 3, 6. Those are all the numbers that divide 6. And then I'm going to come over to the leading coefficient here. And the leading coefficient is going to give me the q values. So the leading coefficient is 2, and the factors of 2 are 1 and 2. Right? So when I come up with this list, I need to put all the p values over all the q values. I mean, you need to do this really carefully, okay, orderly. So what I like to do is I like to put all the p values over 1 first, and then put all the p values over 2 in the next row. So I'm going to do plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1. There's my first row. Okay, I put all the p's over 1. And now in the next row, I'm going to put all the p values over 2. All right, so plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 6 over 2. Right? Now, what we have to do before we count these up is we have to cross off the duplicates. Right? If they're over 1, it's not a duplicate. All right? But if any of the other ones reduce, then it is a duplicate. So see how 2 over 2 reduces to 1? We already have that, right? So I'm going to cross off 2 over 2 because it reduces. I'm also going to cross off 6 over 2 because 6 over 2 is 3. We already have that 0. We don't want to count it twice. All right, so how many possible rational zeros do we have? Right? Unique. How many possible unique rational zeros we have? 1, 2, 3, 4, 5, 6. But remember, it's not just 6. We have to double that because we have positives and negatives. So we have 12 possible rational zeros. Now, of these 12 possible rational zeros, the maximum number that's going to work is equal to the degree. So this polynomial has 3 zeros. Okay, only 3 of these are going to work. Or maybe 2 of them are going to work and 1 of them is going to work twice, just like before. So I'm going to get ready to look at how many of these zeros work. All right. So I'm going to go to the calculator and I'm going to graph this function. Right? 2x cubed plus x squared minus 13x plus 6. Right? Now, instead of going to the table and plugging all these in, I'm just going to look at the graph. All right? Because x-intercepts and zeros are the same thing. So I have it crossing once, twice, 3 times. All right? So it crossed the x-axis 3 times. This one is at -3. This one's between 0 and 1, and this one is at 2. So the ones I know for sure are -3 and +2. So -3, +2. Now, because I have 2 zeros with only 1 0 left, I know this has to be a fraction between 0 and 1. Right? So if I look at my fraction values between 0 and 1, it's probably 1/2, right? Because that's the only one I have between 0 and 1. So I'm going to go to my table real quick just to double check. And I'm going to make sure that 1/2 works. So notice I'm just typing in 1 divided by 2 here. And if I hit enter, I do indeed get a 0 for the y value. So I found all 3 zeros, -3, 1/2, and 2. All right, so let me write that down, 1/2. Okay. Now if you're using the online calculator, I will show you how to get the halves. It's just a matter of when you do the change in table, make the change in table 0.5. Okay, and that'll get you like, -7, -6.5, -6. So make your change in table to 0.5 if you want to use the table to find this 0. All right, so here we go. We're going to write the factors, right? The factored form. So if -3 is a 0, x plus 3 is the factor. If 2 is a 0, x minus 2 is the factor. If 1/2 is a 0, x minus 1/2 is the factor. Now you can't leave it here. And the reason why you can't leave it here is because if you were to multiply this out, you wouldn't get this polynomial, right? Just looking at multiplying the first terms, x times x times x is x cubed. I need a 2x cubed, right? And if I were to multiply 3 times -2 times -1/2, I would get 6, I would get +3. And I need a +6, right? So you can't leave fractional factors, all right? So no fractional factors allowed. So how do we get rid of, scoot that over. How do we get rid of this fraction? Well, if the fraction is 1/2, I just need to multiply it by 2, all right? So what I'm going to do is I'm going to take this factor and I'm going to multiply by 2 on the outside, all right? And that's going to clear up this fraction. I don't need to multiply the other 2 factors, just the one with a fraction, all right? So now I get x plus 3, x minus 2, and then my factor without a fraction would be 2x, right? After I distribute the 2, 2 times -1/2 is -1, okay? So these 2 factors yield the same 0, right? And this factor is the one that is going to get me the right leading coefficient, the right constant, and as a result, the right middle terms as well. Because x times 2x is 2x cubed. 3 times -2 times -1 is +6. Okay, everything lines up. So what I'd like to show you is another way of thinking of this. Okay, so if 1/2 is a 0, that means it was a solution, right? That means x equals 1/2 is a solution to this polynomial. Now, if I were to reverse solve this, okay, and go backwards, the first thing I'd want to do is multiply both sides by 2. So now I have 2x equals 1, right? Reverse solve, meaning get the 0 over here and everything else on the other side. So now to move this over, I'm going to subtract 1 from both sides. Kind of ran into my work there. And I get 2x minus 1 equals 0. This is the factor that led to this solution, x equals 1/2. So I don't expect you to reverse solve them, but I did want you to see that that's why. Okay, we're not just magically multiplying by 2. There is a reason why we need this 2x minus 1. All right, so I'm just going to keep working examples. This handout has, like, if you noticed, 7 to 9 pages. I don't remember off the top of my head now. But it's just a lot of examples, and it's doing this process over and over, okay, and over. All right, here we go. This example, the title says using rational zeros theorem and the quadratic formula. Okay, so we might have to do a little bit extra work on this particular example. But the first step is first to find all the rational zeros. Okay, so I still want to come up with my possible rational zero list. That's always where we're going to start. What are my possible P over Q values? Right? So the P values come from the constant, right? And the constant is 10. And the factors of 10 are 1, 2, 5, 10. Right? Those are all the numbers that divide 10. Now we're in luck here because the leading coefficient is just 1. So we only have one Q value. So it looks like all our possible P over Q's are just going to be whole numbers. 1 over 1, 2 over 1, 5 over 1, 10 over 1. But don't forget the pluses or the minuses. Right? Plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 5 over 1, plus or minus 10 over 1. Right? Now, this particular polynomial is a 4th degree polynomial. So it has 4 zeros. Right? And so it would be nice if we found all 4 in this list, but because it said we're going to have to use the quadratic formula, I'm not so sure. So the best case situation, guys, is if you find all the zeros in this list, because that's easy. You just write them as factors and you're done. Okay. The second best situation is if you can find all but 2. Because if you can find all but 2, the last 2 zeros, you can use the quadratic formula. Okay, so we really have to find, of the 4 zeros, we have to find 2 in this list. Right? So, and then the other 2 we can use the quadratic formula on. So let's see which ones work. Okay, so I'm going to get my calculator. I'm going to plug this in and then look at where the graph has x-intercepts. Right, x to the 4th minus 5x cubed minus 5x squared plus 23x plus 10. All right, so now if I click graph, hopefully this graph crosses the x-axis twice. 1, 2, 3, 4. All right. It crossed 4 times. But the good news is it crossed 2 times right on one of those tick marks. Okay. These little fractions are probably the irrational zeros that we're going to use the quadratic formula for. So the zeros, the whole number zeros, the rational zeros I see are -2, and 1, 2, 3, 4, and 5. Okay. So notice in our list we didn't have any rational zeros. So these fractional rational zeros are not true fractions. They're irrational zeros, right? So we found 2 of our 4 zeros, right? So what do we do now? Okay. We need to break this 4th degree polynomial down to a 2nd degree polynomial. And the way we're going to do that is with synthetic division, right? I'm going to synthetically divide by both of these zeros, right? Now, not only am I going to synthetically divide, I'm going to do what I call piggyback the synthetic division. So don't get too far ahead of me here. Now, it doesn't matter whether you divide by -2 or 5 first. It'll still work, okay? But I'm going to divide by -2 first. So I'm going to list out my coefficients. 4, 3, 2, 1, 0. All right, I don't need any placeholders. So we got 1, -5, -5, 23, and 10. Okay, skip a space, draw a line. Now remember, the first step in synthetic division is to go ahead and add the 1 down. Right? Add down first. Multiply, put it in the next adjacent spot. So -2 times 1 is -2. Add down. Okay. Now we're going to do -2 times -7 and get 14. Add down. Now we're going to do -2 times 9, which is -18. Add down. Now we're going to do -2 times 5, put it in the next adjacent spot, add down. So notice this is our quotient, right? And then the last number is our remainder, so we had a remainder of 0. If this is a 0, your remainder should be 0, right? If you don't get a remainder of 0, you either forgot a placeholder, using the wrong 0, added something incorrect. Okay, you absolutely need to get a 0 remainder. So now what I'm going to do is I'm going to divide 5 not back into the original polynomial, but I'm going to divide 5 into this answer. Okay, I'm going to divide 5 into the quotient, right? So I'm going to put 5 in a box here, and when I draw this line, I'm going to stop at the 5. Do not divide into the remainder. Okay, so every single time we piggyback this synthetic division, our division process should get 1 column shorter. Right? So just divide 5 into the quotient. So now if 5 is a 0 of the polynomial, 5 will be a 0 of the quotient as well. So this one should get us a 0 remainder. All right? So first step, add down. Multiply times 5 in the next adjacent spot, add down. Multiply times 5, put in the next adjacent spot, add down. Multiply by 5, put in the next adjacent spot, add down. Okay, so we did get 0 remainder again. All right, so this here is the quotient. All right, this is what's left after we divide x plus 2 and x minus 5. So remember, in synthetic division, it gets 1 degree less, right? So we started off with an x to the 4th. When we divided the -2 out, this would be our x cubed coefficient. And so then, when we divided by 5, this is our x squared coefficient. This is the x coefficient. This is the constant. And this is the remainder, right? So for right now, right, we have factors. If -2 divides it, x plus 2 is the factor. If 5 divides it, x minus 5 is the factor. And then this quotient here is our last remaining factor. Okay, so if it asks for the factors, as long as none of these factors factor anymore, then you're done. So x squared minus 2x minus 1 does not factor. There aren't any numbers that multiply to -1 and add to -2. Okay, so this is completely factored because none of the factors factor any further. But it does we do need to find all the zeros, right? And at this moment, we only have 2 of the zeros. So what I need to do is I need to find the zeros of this quadratic. All right, so I'm going to go over to the side here, and I'm going to set this quadratic equal to 0, and I'm going to solve it using the quadratic formula. All right, so just in case you don't remember, right, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. I bet you missed that song, didn't you? All right, here we go. So a is 1, b is -2, c is -1. So if I do -b, I'm going to get a +2 plus or minus the square root. Negative 2 squared is 4, minus 4 times A times C, all over 2A. Okay, so I'm going to get 2 plus or minus. Now underneath the square root, a negative and a negative is positive. So I really have 4 plus 4, which is 8 here, all over 2. Okay, now be careful. We need to simplify this before we start canceling. Okay, so the square root of 8 is the square root of 4 times the square root of 2, right? And the square root of 4 is 2, so I get 2 rad 2. So I'm going to get 2 plus or minus 2 rad 2 over 2. That's a lot of 2's, right? But it's the 2's on the outside that cancel. And both of these terms need to cancel by 2, right? Because you can't just cancel one side and not the other side on the other side of that plus or minus sign. So if you wanted to, we really have 2 over 2 plus or minus 2 rad 2 over 2, right? And you might split that up before you start canceling so that you don't get the wrong answer, right? So this is going to reduce to 1, and the 2's on the outside is going to reduce to 1. Sorry, I ran out of room over there. Let me write it over here. So I'm going to get 1 plus or minus rad 2. Okay, these are my other 2 zeros. So when I go up to my zeros list and I list out these zeros, remember they have to be in a comma separated list, and you can't do plus or minus, so we're actually going to do 1 plus rad 2, comma 1 minus rad 2. Right? These are all the zeros of the polynomial. Right? These do happen to be all the real zeros. Okay. Real zeros are the rational and irrational zeros. If the 0 is not real, that's because it's imaginary, right? And in section 3.4, they don't want you to list imaginary zeros, right? So all the real zeros here, here's all 4 of them. Okay, guys, I think I'm going to break this video off, and I'll do more examples on the next video. But this does give you a pretty good head start in doing that homework from 3.4.